Well, hello everybody. In this presentation, I want to say a few things about inference and many other things. So, let's start out with a little bit of an overview of some of the concepts that we need to know about when we talk about inference. Like understand the infrastructure, if you wish, of this term. So these are all links to Wikipedia pages. So let's start out with the first one. So inference is about steps in reasoning. We may infer something from something else, something from some given premises, and then some consequences that we're interested in. So that's what inference is. So it's actually fairly technical. Reasoning is a little bit more general. So inference certainly is part of reasoning, but we can figure stuff out, perhaps by, I don't know, using our gut, by making some sort of like leaps about stuff, by letting things germinate. So reasoning is sort of like, generally speaking, thinking about stuff. If we want to be technical, and as AI folks, as computer science people, we do want to do that, we need to have some rules of inference. So those rules that logicians studied show us, like if P then Q and P, then we can infer Q, so modus ponens is a rule like that. So once we have these rules of inference, we're interested in, let me go to this one here next, proof systems. So proof systems is a very technical thing again. It's just simply a system that enables us to use the rules of inference properly. And we'll have a look at one of those things later today. Whoopsie, I meant to show you this one. No, that was it, proof system. Let's go to logic here very briefly. There are different logical systems. Logic technically is the study of valid reasoning. And so logicians develop these different logics, so to speak, that enable them to study valid reasoning. We'll be looking at two systems here today and tomorrow. One of them is predicate logic, and the other one is propositional logic. When we do things in computer science or in logic or in AI, we want to be very formal. Long story short, a computer doesn't understand anything. So we need to be very, very picky, very precise. We need to pick data structures. We need to implement things through procedures. The computer would like to have things that are very, very precise. In other words, formal. We need to represent things, store things in variables. When it comes to formalizing things, we typically have a syntax. Syntax from natural languages. If you learned a second language, you kind of like learn some of the words that are part of it, and you learn rules and recipes on how to make sentences. So that's all in the syntax. But the syntax tells you how to build what they call well-formed formulae and to manipulate them, but doesn't tell you what these things mean. So semantics is a formal way of assigning entities of a domain to our sentences. So for example, if we have a sentence, human Socrates, then we might be able to identify some people among all the humans as a given Socrates. And we may do this the right way or the wrong way, and depending on how we do it, sentences are either true or false. So semantics is about the ability to assign truth or false systematically to well-formed formulae as well as to proofs. Is the proof valid or not? The proof, you have given those things in math quite a bit, is a systematic argument, typically a formal argument, that enables us to show that something follows some premises. Now I should tell you that in mathematics sometimes proofs are very, very formal and sometimes they're not. All of them are proofs as long as they're systematic and as long as they convince the reader that something is true, that something follows from something else. And finally, we make the connection to AI, where we sort of like show that logic, so to speak, logical systems are a form of knowledge representation. As a matter of fact, they were some of the earliest knowledge representation systems used, including for planning. So they used theorem provers to do planning. And as such, they're sort of like the atom, so to speak, of knowledge representation. So they enable us to study what knowledge representation is all about. So the essence of it. All right, so a quick overview. So let's move on and so like study some of these things in more detail. When you do formalization, you kind of need to understand the limitations of what we can do here. So down here we have the world, and there are certain aspects in the world, and we may see that, oh, well, geez, there's a leaf, and it's turning yellow or red or brown, and there's some wind, and suddenly that leaf falls down to the ground, right? So we may sort of like realize that, oh, wait a minute, there are all these other leaves, I bet they're all going to come down here. So these are aspects of the world, and then we may infer something else, or we may sort of realize something else, some aspect of the world, like, wow, that tree is not going to have any leaves here sometime soon. So it follows because, well, we know about biology and winds and things like that. So these are things in the real world that we can observe. Now, a lot of times these observations sort of like requires us to express things, at least internally, to sort of realize something. But when we go to representations, we definitely need to represent things. And so we use sentences. So we may use a sentence, that leaf is yellow. That leaf is red. It is fall. It is windy outside. It is raining really hard. So those are all sentences that we can do. And then we can take some more sentences from biology that sort of like tell us what happens in the fall to the leaves and to the trees and to the sap. And then we may use some formalism. We may use some symbol manipulation to derive new sentences. A simple one is, there's a yellow leaf and there's a red leaf, which we can write down if we have the sentence, there's a yellow leaf, as well as the sentence, there's a red leaf. So we can push, we can derive many new sentences, and then we look at some of these sentences and say, aha, here's something interesting going on about the world. So notice that there are two ways to sort of like derive new knowledge, if you wish, or to make explicit what is already implicitly contained in the given information. So that's what inference is about, to make things explicit that are implicitly contained. And sometimes the stuff that you make explicit is earth-shattering, and sometimes it is not. So this then here is what we have to do as computer scientists. We sort of like have to represent things, and then we have to use our code, our software to come up with new representations, and then somebody looks at these things and say, aha. So notice that this aspect of representing things in the world is something that humans have to do. All right. Now there are some machines, that we can set up to sort of like realize some things about the real world, but certainly most of the time we are the ones who do the interpretation. The interpretation from sentences to the real world, and the representation or formalization from the real world to sentences. Again, if we looked at AlphaGo, they certainly let the system sort of realize important things about the way to play Go, certainly about strategy. All right, so there we have some formalization. Now, even in science, I want you to understand that a lot of times the debate is not about what follows from something else, but this aspect over here, and where we may see the world just differently, right? Politics is a good example. I mean, we're sort of like, there's an aspect of the real world, and some people interpret this way, some people interpret that way. And then they drive new things and have campaign slogans and stuff like that. All right, so let's move on a little bit to logic. So we're going to be looking at two systems here that are very prevalent in logic, but there are many other logical systems. One of them is propositional logic, and the other one is predicate logic. So in propositional logic, we only have propositions as well as Boolean connectives and something else that we'll see in a moment. So a proposition is a formula or a sentence, a well-formed sentence typically, and we'll talk about syntax and semantics tomorrow, to which we can assign a truth value. So here's some examples. The moon is made of green cheese. What's the truth value? Well, I think it's false, last time I checked. If you're a fan of Wallace and Gromit, you know that some of the planets are actually made from cheese, but not from green cheese. I think it's Wensleydale. I am a millionaire. Well, that happens to be not true either. Block A is a cube, or written slightly different, cube A. The sun is out. So these are all things to which we could potentially assign a truth value. It's not a question, it's not a command, it's not an acknowledgement. These are things that have subject, predicate, object, pretty much. Now, in predicate logic, we have predicates. Now notice that we kind of had a predicate over here, cube A, but in propositional logic, we don't have variables, we only have constants. So that's kind of really, really important. And as a CS, you know the limitations of code that can only have constants. So with predicates and quantifiers come variables. I mean, that's really a key thing. And so these variables enable us to instantiate it with many things, and some of the stuff we will see tomorrow when we talk about semantics. So here are some examples. For all x, if x is a moon, then x is made of cheese. For all x, if x is a human, then x is mortal. There exists some x such that that x is a human, so there's a human. And then again, something that we have seen already in propositional logic, Socrates human. So again, in the system that I will show you later on, we will see propositions like this. And technically they're predicates, but they're not part of predicate logic, because in order to do predicate logic, you do have to have variables and quantifiers. There are two quantifiers that we see in first-order logic, all and exist. And then there are other logics that do things like most and some, things like that. So like trying to capture the fact that things are not always true for everything. So as we can see then, predicate logic is much more fine-grained than propositional logic. So let's have a look at the sentence again, all humans are mortal. In propositional logic, we would represent it with a constant, say P. So like say P is this sentence over here. If you want to have a handy mnemonic, then you could represent the sentence with all humans are mortal, but it's just a different kind of constant. In predicate logic, we would write for all x, if x is human, then x is mortal. And again, the quantifiers and the variables enable us to refer to entities in our domain. That's part of semantics. We'll talk about semantics tomorrow. So here's a different kind of sentence. Socrates is a human. Again, in propositional logic, we would represent it with some other constant, say Q, or again with something handy, say Socrates is human, or with human Socrates. In predicate logic, for sure, we would do human Socrates. I should probably not capitalize these things. All right, so quick overview of propositional and predicate logic. We will see more about this as we go along. So let's see. So what's the difference then in terms of usage between predicate and propositional logic? So in propositional logic, going back to the old P and Q, there's no relationship between P and Q. So we cannot infer things like Socrates is mortal, something that we can do with predicate logic. So if we go back to the sentence, all x, all humans are mortal, we would represent it like this, right? All x, human x implies mortal x. And what we can do is we can sort of say, well, geez, you know, this Socrates is a dude that is part of our domain, and it's that dude. I pointed to something right now. And so we can instantiate the sentence with Socrates. So we would have human Socrates implies mortal Socrates. Together with the sentence that we already know, human Socrates, we can then infer that Socrates is mortal, like that. Okay, so again, we instantiate this thing. This is called modus ponens. Human Socrates implies mortal Socrates. We also know that human Socrates. So we know we can infer mortal Socrates. So notice that's what I mean by it's more fine-grained. We can sort of like infer things. We can get at things that we couldn't get with propositional logic. There are still some things that we can do with propositional logic, and we'll see about that in a moment. So let's have a look at the rules of inference for propositional logic, and predicate logic we'll have a look at tomorrow. There are only 4 additional rules. So what we're going to do is we're going to look at the following Boolean connectors: and, or, negation, conditional, biconditional, and then we're going to look at the contradiction system symbol. That's not a Boolean connective, but it's something that indicates that, oh no, all truth fell on his head. So notice it's an upside down T. T is true, right? And so it fell on its head. It's all wrong. Things went horribly bad, right? Now, here's the interesting thing. It's very systematic. For each of these items, mostly connectors, we have 2 rules. One that introduces it and one that enables us to remove it. So we're going to be looking here at 1, 2, 3, 4, 5, 6, 12 rules of inference. And then for predicate logic, we're going to add the quantifiers. There exist, and for all, and we have 4 additional rules. So let's see how this thing works. Now again, I want you to understand, this is all stuff that can be implemented. This is stuff that a computer can handle. This is very formal. So, and introduction. So if we have some propositions in our proof, like P1, P2, blah, blah, Pn, then what we can do is we can write down a formula that when we AND them all together, P1 and P2 and blah, 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 Pn. Okay? So if I know that the moon is made of green cheese, and I also, well, know or else establish somewhere in my proof I am a millionaire, then I can write down the moon is made of green cheese and I'm a millionaire. All right? Yeah, I know it's not rocket science, but it's handy for some proofs. And elimination. If you have a compound statement with lots of ands in it, P1 and P2 and blah, 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 Pn, then you can pick any of those things and write it down all by itself. So again, going back to the old example, the moon is made of green cheese and I'm a millionaire, then I can write down I'm a millionaire. So the idea is if the compound statement is true, then each of the only way we can make this true is if each of the individual ones are true. And so we can pick out any of the individual ones and write it down. So pretty handy stuff. So there is AND introduction and elimination. Let's have a look at OR introduction. That's kind of like a cool kind of rule. So suppose we have some proposition that appears in our proof, then we can write down P1 or blah, 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 or PI or PN. So notice that the PI is in here and we can sort of like pad it with as many other statements or as we want to. So because if this one is true, then obviously anything we add to it by an OR also has to be true, even if all these are false. The entire compound statement is still true. Yeah, sort of like dilution of information a little bit, right? So OR elimination, this one is really cool. It's a bit tricky, the way we have to apply it, but it's in essence proof by cases, something that you have done in math. So when we do OR elimination, it is very important that we know what the cases are. We can't sort of like pick some arbitrary cases, you know, holds for this and holds for that. No, you have to say the only cases that are important or that we know of or that we know to be true is A and B and C and D and E. All right, and then you have to prove whatever you want to show from each of those A, B, C, D, E. Okay, so we have to know what the cases are. It has to be stated somewhere in the proof. And then we have to prove whatever we want to show from each of the cases. So let's have a look at that in more detail. So suppose that P1 or Pn, blah, 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 appears somewhere in our proof. Then, and we can prove for each of these Pi that S follows from it. So for P1 and P2, P3, all the way to Pn. Then, since we have shown something for each of these individual cases, and we know that only this statement is true, then we also know that S is true, right? Because we have shown that no matter which one of these things is true, S follows from all of them. And such, we can write down S. I will show you a proof later on today, and we'll actually use this rule in there. Negation introduction, that's a proof that you have seen many times, I'm sure. It's a proof by contradiction. So suppose we have a subproof, we say assume P is true, and then we show a contradiction, then we typically write down not P, right? So well, that's what we can do. We're authorized to write down what not P must be true. So it's a proof by contradiction. And elimination, if you have a double negation, you can always knock it out. And so sometimes over here we have a not P in here, so we want to prove that something is not true, and we derive a contradiction. So then obviously we would write down not P, and then we can go down to the P by this rule over here. All right, very good, humming along. I love this thing, right? So the contradiction introduction. If in a proof there's a formula P as well as a formula not P, then we can write down the contradiction. Because in this case, the information is inconsistent. In logic, we can't have something that is true and false, right? So not P being true means P is false. It just doesn't work. The information is inconsistent. With inconsistent information comes something else. We can write down anything. So the contradiction elimination means if you have established this one over here, you can write down anything you want to. It's a joker, right? Whatever you want to write down, you can write down. And again, as you can sort of like imagine, that's pretty bad. We don't want that. Now, mind you, that humans are inherently inconsistent. I mean, for any of us, if somebody probes us long enough, we'll probably come to a state where we make a statement P as well as not P, and then they can say, hey, yo, you're inconsistent, right? And we are. we really are. But we still function really well, don't we? Let's see. Oh, yep. Let's see. Conditional introduction. So this is something that we also do quite a bit. Suppose in a subproof, this is the main proof. This is a Fitch-style proof system, by the way. and we sort of like say, well, let me assume P is true. You can assume anything, right? You can assume the moon is made of green cheese. You can assume my dad is a millionaire. Lots of stuff. It doesn't matter. But suppose we have an assumption and we derive something else based on this and other things that we have in our proof. Then we have shown that if P is true, then Q is true. In other words, P implies Q. Now notice that all we have shown is a connection that might exist, say, in nature or somewhere. So we can write down P or Q. It doesn't mean that P is true. So we can find out that, oh, if the moon is made of green cheese, then I am a millionaire, right? So we might be able to establish things, but that doesn't mean that A, the moon is made of green cheese, or that I'm a millionaire. I just simply established a connection in nature. If I sit underneath the apple tree and it's fall and the apples fall down, then an apple is probably going to fall on my head, right? If then. It doesn't mean that I'm sitting underneath an apple tree or that I even have an apple tree, right? Or that apple tree has apples. So that is something we do quite a bit in science. So implication introduction. Implication elimination, that's a famous modus ponens. So in a proof you have P as well as P implies Q, then we can write down Q. We have seen that earlier with Socrates is human. If somebody is a human, then they're mortal, so we were able to write down Socrates is mortal. Actually, technically we had if Socrates is a human, then Socrates is mortal, and so we were able to establish Socrates is mortal. Great rule. By conditional introduction, fairly straightforward. If you're able to derive Q from P and P from Q, then you can write down that they're equivalent. Elimination, suppose you have P is equivalent to Q or Q is equivalent to P, either of those, as well as P, like we have over here, then you can write down Q. Okay, so it makes a lot of sense. So what I want to do now is I want to give this proof over here using only the rules of inference that we have seen over here. So typically I ask you to do this in class and I'm able to walk around and so like talk to many of you about some of the non-syntactic ways in which you prove these things. So some people make assumptions, some people sort of like look at this thing and argue about it, and all of them are valid reasoning, right? Because, well, it turns out that this conclusion here follows from these three premises, or this sentence follows from these three premises. But we want to do that just by pushing symbols. So we don't even know what cubes are or what small is. That's what we want to do. So I'll have that in a separate presentation. So please have a look at it. I will see you then. Bye.